Hello everyone. Today we're going to learn about derivations. Derivations are a skill that you're definitely going to need for the AP exam. They are very useful in physics in general and in other areas of science. So let's dive into what they actually are. So what do I mean when I say derivations? So derivations are an extension of formula rearrangement. So we did formula rearrangement earlier. That involves combining two formulas, substituting variables where necessary. So what is this actually going to look like if you're given a problem? How are you going to recognize that you need to do a derivation? So the problem will often be written as, given formulas, 1 and 2, solve for blank, some variable, in terms of, and then other variables. So what in terms of means is that you can only use those variables in the final answer. You may not use any other variables. So there are some variables that might show up in the formulas that you have that you're not allowed to use in your final answer. You can, of course, use numbers, fractions, pi, and other constants. So any constant is fair game. Now the reason we might want to do this is because when you take data, you might only be able to take data on certain things. What can you actually control? What's your independent and what's your dependent? What are you measuring? And from those data points, you might want to draw a conclusion about the physical system. So you might want to figure out what, let's say, the mass of an object is if you take force and acceleration data. So you're going to need to figure out how to derive a formula that will give you the variable that you want on the left-hand side of the equation, and then the other stuff on the right-hand side that contains the variables that you actually took data for. So let's look at a simple example. Let's say we have two formulas that represent electricity. Power, P equals IV, current times voltage, and current is defined as voltage over resistance, V over R. So when you're dealing with, these are DC circuits formulas. So when you're dealing with DC circuits in the real world, there are two out of these four variables that are directly either controllable or measurable. So the first one is voltage, V, and voltage is a good one to have to take data for because you can control the output voltage of a battery or a power supply or whatever it is that you're using to provide power to the circuit. You can control the voltage. So that's the thing that we can control or that we can measure. And then R, the resistance, is a property of the material that you happen to be using. So every material has an inherent resistance depending on a couple of factors. Normally we have these ceramic resistors that we use in circuits. We're going to learn all about this later. But let's say I only can get data for voltage and resistance, and I want a formula that gives me power. So power is something that is not quite directly measurable. And the variable that we don't want to use, we can't use I, because I is not something that is easily measured. It can be calculated, but it's not easily measured unless you have an ammeter. And if you don't have an ammeter and you want power, we need to figure out a workaround. So what I'm going to do is I'm going to substitute the expression that represents I, current, into the power formula. So if we look over here, we have an I in this formula, and we also have V over R as the definition of I. So we can just put in this formula where I is supposed to go. So here it is. We went from P equals IV, then we substituted in the formula for I, V over R. And then if we simplify it, we have two V's and an R, so power is voltage squared over resistance. So that's our first derivation. We have come up with a formula that takes voltage and resistance data and pumps out power data. All right? So that's the first really simple example of a derivation. Let's go to a different one. Let's talk about pendulums. The period of a pendulum is written as t, that's the variable for period. Period meaning how long it takes to complete one cycle. So one swoop down and back, that's the period of a pendulum. So you would time that motion. And that t equals 2 pi square root of L over g, where L is the length of the string and g is gravity. It can also be expressed, so period can also be written in terms of the frequency of the oscillation. So T equals 1 over F, where F is frequency. And I'm asked to derive an expression for L. I want L in terms of G, F, and pi. And of course, any other numbers that we happen to have. We do have a 2 in here, so that's going to factor in. What we can't use is T. We need to substitute the frequency formula into the period formula. So we started with, we have these two things that mean T. So here's one T, and here's the other T. And so this works because of the following reason. We can just set these equal to each other because if A equals B and B equals C, then A equals C. So if T equals one formula and T equals another formula, those two formulas can be put right back to back on either side of the equal sign, and that's what we've done right here. So we get 1 over F equals 2 pi square root of L over G. So that's our first step. We just substituted in the formula for T. The second thing we're going to need to do is move that 2 pi over. So we're going to divide by 2 pi on both sides. We're left with 1 over 2 pi frequency equals the square root of L over G. We're going to square both sides to get rid of that square root on the right-hand side. So what we would go ahead and take each of these and bring them to the power of 2. So that means on the left-hand side we have 1 over 2 pi f, all squared. And then, of course, this power of 2 gets rid of that square root. So we're left with just L over G. And the last modifier that's happening to L is that it's divided by G. So we multiply by G on both sides, and we end up with a final formula of G times 1 over 2 pi f, all squared, equals L. So we have successfully come up with a derivation that only uses f, g, and pi, and of course constant 2. So that's our next simple example here. Okay. So what I want you to give this a shot. So you can grab a whiteboard or use a piece of paper. I want you to go ahead and practice this derivation idea. If the formula for electric force is Fe equals K Q1 Q2 over R squared, and Newton's second law is F equals ma, derive an expression for the constant K in terms of the mass of the electron, me, its acceleration, ae, Q1, Q2, and R. So Q1 and Q2 are charges, R is the distance between the charges. And I'll give you a little hint here. F equals ma for an electron can be written as Fe equals me a e, where all of those subscript e's just indicate that we're talking about an electron. So that's what you're going to start with. So I'm going to take like 2 seconds here. I would recommend that you have whoever is doing this pause the video and restart after, let's say, a 10-minute period of time where you can try to work on this problem. Okay, so hopefully you've worked on the problem and now you've resumed the video. So let's give this a shot. And I'm going to write this one out this time. So we have Fe equals K Q1 Q2 all over R squared. And we also, I told you that Fe equals me ae. And we want to solve for the constant K. So that means we want to end up with something that says K equals blank. And we can only use me ae Q1 Q2 and R. So if we're looking at the formula for K, we have a couple of options here. I'm going to do the move around then substitute. So the first two examples that I gave you were substituting first and then moving things around. So I'm going to take a different route here. And I'm going to take the first formula and I'm going to try to get K on its own. So if I start with Fe equals K Q1 Q2 over R squared, I'm going to try to get K on its own. So the first thing I'm going to do is I'm going to multiply by R squared. Right? We always work outside in when we're moving stuff around. So we get FER squared equals K Q1 Q2. Let's bring this up here. So we have FER squared equals K Q1 Q2. To get rid of those modifiers, those Q's, I'm going to divide them both at once. You can do them one at a time if you want to, but this just saves time. Divide by Q1 Q2. So these cancel out, and we're left with FER squared all over Q1 Q2 equals K. So we're almost there. The only thing that we notice, hopefully, is that in here we have an FE, and that is not something that we are allowed to use in this formula. So let's look back and see what we have. Well, we do have this formula here, F equals MEAE. We can use ME, we can use AE, so we can use this. So I'm going to go ahead and substitute in that FE, so we end up with MEAE R squared all over Q1 Q2, and that equals K. Let's double check if we have everything that we need. ME we can use, AE, R, Q1, Q2. We have discovered an expression for K, so we are done with this derivation. Right? So hopefully you figured that one out. If not, I hope that solution was adequate. So feel free to watch this back if you have any kind of questions whatsoever. I'm going to put these notes up on Class Notebook so that you can reference them in the future. So now what I would like you to do is you're going to do the Week 0 Classwork 2 worksheet, which is on derivations. You're going to have a paper copy of the classwork and the homework. So you're going to do this and Week 0 homework. So do Week 0 classwork 2, Week 0 homework 2, and then when we come back to class, we will go ahead and review those topics. So I hope this was useful. Feel free to contact me at any time. I may not respond immediately, but hopefully we'll all come to a good understanding of what this actually is. Otherwise, good luck, and I will see you later.